Today we continue to talk about graphs. We continue to talk about depth-first search algorithms, and we discuss one more application of depth-first search algorithm, a little bit more interesting than in previous lecture and stuff. Go. So, what we talk about today is about connectivity in directed graphs. So, how the connectivity works in directed graphs. If you remember the previous lecture, we discussed connectivity in undirected graphs. In undirected graphs, it's very simple. Connectivity works like this. You have some components. Yeah. So in each component, you have something, and here something. And two vertices are connected if they belong to the same connected component. So if you take any two nodes and look on the connected components of these nodes, if you have the same connected component, then these two vertices are connected. If you take vertices from two different connected components, they are not connected. So it's very simple. In directed graphs, it's a little bit more complicated because this relation is not symmetric. So you may have some node V and some node U. So U is reachable from V, but V is not guaranteed to be reachable from U, so it's not symmetrical. So you may have some strange constructions of this connectivity. And what we will talk about today is about how it works in directed graphs if you look on the big picture. Go. So let's look on the following relation. Let's say that two nodes are double connected. They be connected. Let's say be connected. I'm not good in English terms actually. Let's say two vertices are be connected if you have the strongly connected. Yeah, let's say they're strongly connected. If you have both paths, so if you can go from V to U and you can go from U to V. So yeah, we will not have stream on Friday again, like I explained before. I will be very busy on Friday, so we have lecture today instead of Friday. So let's say that two nodes are strongly connected if I can go both ways, if I can go from V to U and go back. And this relation is actually symmetrical, and that's good. And it is also transitive, because if I have three nodes and I can go from V to U and back, and I can go from U to say W and back, then I can go from V to W and back. Yes, just using this path. So I can go from here using this path and this path. I can go to W, and then I can go back just using this path and this path. So this relation is actually symmetrical and transitive. So again, it will form some equivalence classes, yeah, like before. So if you look on the all nodes, they will be split into some sets. Such in each of this set, all the nodes are strongly connected to each other, and these components are called strongly connected components. Well, let's draw some graph. For example, let's put some numbers actually. Let's see, 1 and 2 and back. Well, let's see. Let's put 2 here. Let's put 5 here, yeah. And something here, just 2. Let me think. So I want it to be here, and then let's do 2, and then let's say 4 here, and 6 here. And I want it to go there and go back. Yeah. I'm just thinking what I want to achieve. Now, let's do it like this. Let's put this there. Now let's put 4 here and 6 here. Like this. And then we have 1, 2, 3, 4, 5, 3, yeah? And let's put 3 here. Like this, for example. Yeah, that's fine. So let's look on this graph. In this graph we have several connected. Oh, let's put some mouse. So it's no, it's not interesting. Let me think. Just a second. I wanted to go here and then back. Sorry, I just want I just want to make interesting graph, so something interesting is going on. I'm going to compare. Yeah, let's do it like this. Let's go. That's there and then go back like this. Yeah, sorry. Yeah, now it must be fine. Let's put something. Let's put 7 here just to make it. Yeah, something like this. Yeah, now it's fine. So let's look on this graph. So we have this graph. In this graph, we have some set of nodes such that in each of this set, all nodes are strongly connected to each other. For example, if you look on these 4 nodes, in these 4 nodes, we have a path from every node to every other node. So this is strongly connected component. For example, from these 3, if you want to go this 7, you go like this. You go here, here, and here. If you want to go back from 7 to 3, you go here, here, and here. And so on. From 3 to 2, from 3 to 6, from 3 to 7, and back from 7 to 3, from 6 to 3, from 2 to 3. So you have paths from every node to every other node. So these 4 nodes are strongly connected component. And it's easy to see that all other nodes have no connection to these nodes. So you cannot go from this part of the graph to this part of the graph. So these 4 nodes belong to the same strongly connected component, and these nodes belong to some different strongly connected components. Yeah? So what happens in this part of the graph? So you have these 2 nodes. From these 2 nodes, you can go both ways. So these 2 nodes are another connected component like this. And you have this single node. This single node is a strongly connected component of 1 node. It's possible. So some strongly connected components maybe just consist of a single node. That's fine. Like this. So this graph is split into 3 strongly connected components. Now, what you can do? You can enumerate these strongly connected components. Let's just label them with letters just for clarity. So let's say this connect component is A, this is connect component B, and this is connect component C. And now what you want to build is to build another graph which consists of these strongly connected components. So let's build the following graph. For each strongly connected components, let's build 1 vertex. So we have this vertex A, vertex B, and vertex C. And now we will build edges such that you can you see this? Isn't it too light? Something darker. So for these 3 vertices, you build the edges if these connected components have the edge between them. So here you have this edge from 3 to 1. 3 belongs to A, 1 belongs to B. So we need to make edge from A to B. So this edge is now here. Similarly here, so you have edge from 6 to 4. 6 belongs to A, 4 belongs to C. So we have edge from A to C. And here you have edge from C to B. So you have to make edge here. That's all. This graph is actually important. This graph called the condensation of this graph. This condensation. That's all about that's all about terms. So that's all we need to know basically. Again, let's call two vertices strongly connected if we have both paths from V to U and back from U to V. This relation is equivalence relation, so all your nodes will be split into some equivalence classes. This equivalence class is called strongly connected components. Inside each strongly connected components, all the nodes are connected to each other. Then you can split into strongly connected components and build this graph. This graph is called the condensation. So each strongly connected component is just squeezed into one single node. And you build this graph. That's all. Now, what's interesting about this graph? Interesting about this graph is you can have cycles in this graph. So in the condensation of any graph is always a cyclic graph. Why you can't have cycles in this graph? No, it's easy to see. So if you have cycle in this graph, it means that you actually any cycle is actually a strongly connected component. If you have a cycle, then in this cycle you can move from any node to any other node. So all vertices in the same cycle should belong to the same strongly connected component, right? So in these condensations, each strongly connected component is just squeezed into one single node. So in this condensation graph, you can't have any cycles. So this condensation is always some acyclic directed graph. Acyclic graphs are much more easy for many algorithms. So in many algorithms, if you have a cyclic graph, it's much easier to see what's going on, because in a cyclic graph you can make a topological sorting and then run some algorithms and so on. So in many algorithms, the first step is just to look on your graph, find strongly connected components, then build condensation, and then run some specific algorithm for acyclic graphs on this condensation, and then find your result. That's what's good. That's how it works in directed graphs. Okay, that's all about terminology. And now we just need to build the algorithm which finds these strongly connected components. So what we'll do today is to build the algorithms which will take the graph and find all the strongly connected components in this graph. When you find all the strongly connected components, it's easy to build the condensation, yes? Because if for each node you know the strongly connected components and belongs, then it's very easy to build this condensation. You just remember for each node which component it belongs. Now you iterate all edges. You look for on each edge. If these nodes belong to different components, then you just add the edge in condensation, and so on. So after you make this split, it's easy to build the condensation, right? Okay, hope it's clear. That's all. That's the plan for today. Let's go. Let's first build some stupid algorithm. So if you don't care about the time, you just want to build all the strongly connected components. How to do it using depth first search algorithm? What you can do? You can take, for example, node 1. Take node 1. And now you want to find the strongly connected component of the node 1. What you can do? You can take node 1, run the depth first search algorithm, and you will find all the nodes which are reachable from node 1. So, yeah. So these will be the nodes reachable from node 1. Now what you can do? You can run another depth first search algorithm on reversed edges and find all the nodes from which you can go to node 1. So it will be another set of nodes. Yeah? So these nodes will be reachable from 1, and these nodes will be the nodes from which you can reach the 1. Now you can just intersect these two sets. So if some node x belongs to both these sets, it means that this node x should belong to the same strongly connected component as 1. So you just take node 1, run this DFS, take the intersection of these two sets, and this will be the strongly connected component of the node 1. Now you find this strongly connected component, you take the next node for which doesn't belong to this strongly connected component, make the same thing, so you take the node 2, so again, you run this for node 1, run this thing, intersect these two sets, find these two nodes, say they belong to the strongly connected component node 1, now you take the next node which is not marked yet, take for example this node, run these two DFSs for node 2, mark this strongly connected component, and so on. Yeah. So what will be the running time for this algorithm? Unfortunately, running time of this algorithm will be too big, because what's going on? When you just run single depth first search algorithm, you just don't remove these marks. Yeah. So in the previous lecture, we discussed that if you run depth first search multiple times from multiple different vertices and don't remove these marks, then the total time complexity will be still linear, because you only run depth first search from each node only once. But here, this not true, because it may happen that this set is big, so spend a lot of time building these two sets, running these two DFS algorithms. But the intersection of these two sets is small, so this you have a lot of nodes here, but they are different nodes. So some nodes are reachable from one, some nodes are nodes from which you can reach one, but they're different nodes. So you spend a lot of time, but mark only single node 1. It may happen. And this may happen actually for all nodes. So, for example, if the graph is acyclic from the beginning, then that's what will happen. So for each node, you may spend m time to run these two DFSs, and then mark nothing, just single node 1. Yeah, so in this case, the time complexity will be the following. So you run these two DFSs, time complexity will be m, and you do it for every node in the worst case, right? So in the worst case, you need to run these two DFSs for all nodes. So m will be multiplied by n. And that's too much. That's too much. So if you have a big graph, you can do it like this. But fortunately, there are some algorithms which works much faster than this. And one of these algorithms we'll discuss. There are two main algorithms for constructing strong connected components. There is a Tarjan algorithm and Kosaraju algorithm. And we will discuss the Kosaraju algorithm today. It's it's a very simple algorithm. The code will be very simple, and the time complexity will be linear. Cooler algorithm in this area. Let's go. So, the algorithm. So, does matter which one? No, they have the same time complexity. Maybe the constant factor is a little bit different. I'm not sure which one is actually better. I'm not sure which one is better in practice. I believe they are pretty much the same real time, but you may try both. Historically, the first algorithm was invented by Tarjan, but then it's little bit. It uses some magic in the middle. We will discuss this magic when we will talk about big connected components and stuff like this, and bridges and articulation points. We will talk about this. Kosaraju algorithm is a little bit easier to implement and a little bit easier to understand what's going on. So we will discuss it today. The algorithm, very easy algorithm. What we'll do? We will take the graph and then run the same procedure we used when we tried to build the topological sorting. So we will run the depth first search algorithm and put the nodes when we exit the depth first search. So we'll sort the nodes by the time when we exit the nodes from the DFS. Remove this. Let me put it here. So the DFS. So we put DFS. Let's do it. Let's do it like this. Let's do it like this. If it is marked, we return. Then we iterate all edges. going from this node U, call the DFS. We need to mark it. Yeah. We need to mark the node. Then we iterate for all edges out of V, and then call DFS. And then in the end of this DFS, we add this node V to the list of the topological sorting. Yeah, like we did before. Yeah. Let's pick P, add the V. It's not algorithm. No, no. If you have a cyclic graph, this algorithm will build topological ordering. If you have cycles, it will build you something. The interesting thing that it will put the vertices in some order, and this order is actually interesting. We'll talk about why it's interesting. We'll talk about it now. So, for example, in this graph, look again, we call DFS from 1. Yeah. So we call DFS from 1. No, P is just some order of the nodes. I will add this node V into this order. I actually need to reverse it, so I will add them from right to left, but it's you'll see in a minute. So we run DFS from here. DFS goes here to node 5. Now from node 5 there's nowhere to go. Yeah. So we exit. So let's just mark all the edges I visit. So I start here, go to 5 using this node. Now it's nowhere to go from this node 5. So let's put the marks back. So I mark node 1, then go here, mark node 5. Then it's nowhere to go from node 5. So this DFS exits. So I need to add node 5 to the list. So I add node 5. Now I go back to node 1. From node 1 there's nowhere to go. So I exit node 1, add node 1 to the list. That's all. Now we take the first unvisited node and start DFS it again, like we did in the topological ordering. So we take node 2, call DFS from node 2. So we start from here, mark node 2, move to node 6, then we move to node 3. Now from node 3 is nowhere to go. So we exit node 3, add node 3 to the list. Then we go back, go to node 4. Exit node 4, add it to the list. Go back to 6, visit node 7. Exit node 7, add it to list. Exit node 6. Exit node 2. So in the end we have this list. Yeah, maybe in Kosaraju you need to build both the normal graph and reverse graph. So maybe it's a little bit, yeah. Maybe the constant factor will be worse for the Kosaraju than in interchannel. But in interchannel you need to build another array for these things. I'm not sure. You need to check both of them. So there are both difficulties in both these algorithms. So which I believe in practice is pretty much the same. Fine. So we have this array P in there. Again, I added to array P from right to left. So I add this one. So if you have vector, you need to just reverse this vector in there. So what's going on in your program? In your program, you do it like this. You iterate for all v from 0 to n minus 1, and just call this DFS for v, and then in the end you reverse array P. Something like this. Yep. So in the end you have this array. And now the magic happens. What is the magic? We will run the second depth first search algorithm on reverse graph. And we will do it in this order. So in this order, we will go and try to run a second depth first search on the reverse graph. So we take the leftmost node here, this node, and try to find all the nodes from which you can reach the node 2. So we'll, again, call the second DFS, let's call DFS 2, because I'm not very creative. So second DFS will work like this. Again, it will do the same. Again, say if mark 2 of v, then we return. Mark 2 of v true. But this 4 will be not iterate all outgoing edges, but on ingoing edges. So we'll iterate ingoing edges of v, and then run dfs2 of u, like this. Again, this is important. So here we go on outgoing edges, here we go on all ingoing edges. For example, in this graph, so we take node 2, we start from node 2, so we're standing here, remove this box. So we mark node 2, then look on all ingoing edge into node 2. So you will use this edge. So you go to node 3, mark this node. To this node 3, you can go from here, you mark this edge. To this node 6, you can go from here. It's already marked. You go back, then use this edge to go here, and that's all. And now the magic happens. Now it's pure magic. So what will happen that this second depth first search algorithm will mark exactly the strongly connected component of the node 2. So if you just run this second depth first search algorithm, for v from 0 to n minus 1, run dfs 2 of p of I. So if we take the first node in this order and call the second depth first search, so depth first search on reversed edges, it will mark exactly the strongly connected component of the node 2. You can see it here. So all the nodes marked by this DFS is actually the strongly connected component of the node 2. So it will mark this node, let's see, this belongs to component A, 6, 7, and 3. 7 and 3. So these 4 nodes belong to strongly connected components of strongly connected component of node 2. Magic, right? We'll prove it in a second. What next? Let's take the next node which is not marked. So let's take first node, leftmost node, which doesn't belong to strongly connected component A. We build this 4. For this node 4, let's call another depth first search on reversed edges. So we start from this node 4. From this node 4, you mark this node 4. Then try to go on all ingoing edges. You have only this single ingoing edge. So you try to go here. This node is already marked. So you stop the DFS, go back, and that's all. So you only mark this node 4, right? And this is exactly the strongly connected component of this node 4. So you mark this depth first search running from this node 4 will mark only this node 4. And that's exactly the strongly connected component of node 4. It was C, it was well, okay, let's call it C just. I don't want to change it here. And now you take the next node which wasn't marked before. So this node 1 doesn't belong to strongly connected component A and B and C, so it must belong to some another strongly connected component. So we take the leftmost node which doesn't belong to any strongly connected component we found before, and run this second depth first search from this node. And it will mark these 2 nodes. So these 2 nodes will complete. That's all. That's the whole algorithm. That's the whole code basically. No, you need something. So if you want to find for each node the label of the strongly connected component, you need to put this label here. And when you call this DFS, you want to put these labels in all nodes. Yeah. So for example, here you want to make you want to count all the strongly connected component. So if it is not marked, you increase the counter, put this counter here, and then put this label to all nodes you visit in this DFS. So you can add second parameter here, the label you want to put on all nodes, yeah, and just put, instead of marks, you just put these labels in all nodes, just to. So what you want to do is to label each node with the label of the connected component, right? So you put labels A to all nodes here, label B to all nodes here, and label C to here. So that's what you want to do usually. Usually it's not labels but numbers, yeah. But just for yeah. Okay. That's all. Now let's prove this actually works. So I want to prove that this algorithm is actually building the strongly connected components. Let's go. Yeah. So to prove this algorithm, we actually need to have some more observations about how depth first search works in directed graphs. So in directed graphs, if you have, let's look on some strongly connected components. So imagine you have some strongly connected components. So you have some strongly connected component A. Let's look on the, so you run your depth first search, this first depth first search, yeah? And at some point, your depth first search will enter this strongly connected component. Let's find the first node you will enter when you visit this strongly connected component. So at some point, you will enter this edge, and this will be the first node of this strongly connected component. So when you visit this first node, all this component is not marked yet. So all nodes in this connected component are not marked. So you have some nodes here. And since this is the first node you enter, so when you enter this node, all these nodes are not marked. Cool. Now let's see what happened before you exit. So your DFS enter this node, then do something, and then go back. I claim that when you exit this, exit the DFS of this node, all these nodes will be marked. So again, the observation is very simple. You have some strongly connected component, and it is not marked. You enter some node V. So when you exit this node V, so when you finish this DFS, yeah, all the nodes here will be marked. So that's the plan. Again, this V is the first node you enter when you enter this strongly connected component. Now, eventually you will visit all the nodes of your graph, right? So you just visit all the nodes of your graph. So eventually you will mark all the nodes of your graph. So let's find the first node in this strongly connected component. I just wait until you say that everything is clear. So let's for some strongly connected component, let's look on the first node of this strongly connected component, which will be marked by your DFS. So what will happen when you enter this node? You do something inside this recursion, and then you go here. You add this V to your list. So the observation is when you exit this node V, all the nodes here will be marked. Let's prove this. It's simple. Let's prove this. So let's take some node inside this strongly connected component, node U. For this node U, since it belongs to the same strongly connected component, there must be a path. Yeah. So there must be a path from V to U, some path. So when we exit this V must be marked. Yeah. So V is marked, but U is not marked. How could it happen? So if V is marked, but U is not marked, let's find the first node on this path which wasn't marked. So, for example, this node X is marked, but this Y wasn't marked. how could it happen? It couldn't happen. No, because when we enter this V, X wasn't marked. Yeah. So when we exit this V, we actually exited this node X as well. Yeah. No, because what happened? We enter this DFS of V. Yeah. And before we exit node V, we marked this node X. So it means that at some point we called DFS of node X, and then go back to recursion and then exit here. Yeah. So we enter this recursion, then enter this recursion, then exit this, and then exit this. So we actually exited this node X. But when we exit node X, we must iterate through all edges from this node X. So we actually must see this edge from X to Y. So we must go to this edge and actually mark this node Y. So it couldn't happen. So if we mark some node X, we must also mark this node Y, because we iterate through all edges from node X. So it could happen. No, it's actually quite intuitive. So if what will happen when you call DFS? It tries to mark everything which is connected to your current node. Yeah. So if you start DFS from this node, it will try to reach everything it could reach, and it could reach all these strongly connected components, because all nodes inside strongly connected components are connected. Yeah. So you actually can reach all the nodes inside this connected, starting from this node V. So when you exit this DFS, it must actually mark everything connected to V. So it will mark all these nodes inside this strongly connected component. Yeah, makes sense, right? Now let's look how it corresponds to this order. So in this order, what will happen? So you enter node V. Now, before you exit node V, you will visit all the nodes inside this strongly connected component. So every node U will be inside this recursion tree, right? So if you look on exit, so every node U must be somewhere here in this recursion tree. So in this recursion tree, you will visit all the nodes inside the strongly connected component. What does it mean? So if you look on this order, so let's look at this. In this order, you have some nodes which belongs to your strongly connected components. So let's see. So you have here, you have some nodes from component A. Which of them will be the node V? What do you think? So again, after you run this first DFS, you have some order of your nodes. So these are all the nodes which belongs to the strongly connected component A. You don't know how it looks, but there are some strongly connected components, right? So let's imagine we look on some strongly connected component. And the nodes of this strongly connected component have these positions in your final order, in this array P. Yeah. So which of them will be the node V? Yeah, fine. So this node V will be the last node we add to array P, because we add node V to array P when we exit the node V. But we will exit the node V at the last. So it will be the last node we exit from all the nodes of this node. So this node V will be here. That's all. That's the first important observation. So for each strongly connected component, if we look on the first node we enter in this strongly connected component, that in this array P, it will be the leftmost node of this component. Cool. That's the first important observation. The second important observation is following. Let's look on two different strongly connected components. So you have some component A and some another component B. And you have edge from A to B. And for each of these components, you have this first node. So you have let's call this first V is the first node of component A, and this U is the first node of component B. So what will happen with these two nodes if we look on them in this array P? So in this array P, we have node V somewhere and node U somewhere. And the observation is that node V is always to the left from the node U. So we have node V here and node U somewhere here. So it belongs to component B. So again, the situation is always like this. Why is this true? No, because when you enter this node V, you cannot leave this node V until you reach something in this component B. Yeah? So when you enter node V, you run across the whole. So your DFS will find everything inside this connect component. And it also will find all the edges going from this connect component. So since you have this edge from A to B, there must be some edge connected something from A to something from B. So when you reach this V, you will find everything inside this connect component, and you will look on this edge. Yeah, because no, this again this node X belongs to this connect component. So before you exit V, you must exit X. And before you exit X, you must see this edge. Yeah? And when you see this edge, you actually find something in connect component B. So some node in connect component B must be to the right from V. Right? And since U is the first node, it also must be to the right from B. Nice. Clear enough? So again, what is the observation? If you look on two different components, and for each connect component, you find the first node of this connect component. So first node is something special. So you have this special node of the first connect component and the first special node of the. So special node is just the first node you enter this connect component. The observation is very simple. If you have some edge from A to B, then first node of B must be to the right from the first node of A. Well, because you cannot exit this node. When you put this V to the node to this P, you try to visit everything from this node V. You can visit something from B, so this B must be to the right from A. It's actually, again, it's quite intuitive. It's actually the same proof like we had when we have topological ordering. Yeah? So it's basically the same thing. What happens is these first nodes of connect components are presented in this P in topological order. So if you leave only first nodes of each connect component, they present in this array P in topological order. So if you have some edge from here to here, then first nodes will be in topological order. That's the whole observation. Clear enough? That's the whole magic. No. Cool. And now the proof. That's all. Now let's look on the first. So let's look on the leftmost element in array P. Leftmost element in array P is the leftmost node in some connect component. So if you look on this leftmost node here, it belongs to some connect component. In this connect component, it is the leftmost node. So since it is the leftmost node, it can't have any incoming edges. Yeah. So this leftmost node belongs to some strongly connected component, and you can't have edges going into this strongly connected component. So you can't have edges like this. No, because if you have edge in going to your first strongly connected component, it means you have some another connected component, and you must have some another vertex which is to the left from your vertex. And if you take the leftmost vertex, it can't have any ingoing edges, right? So if we take the leftmost node in this order P, it belongs to some strongly connected component, and this, well, let's draw this. So this strongly connected component can't have any ingoing edges. So. And now what we do? We try to find everything which all the nodes from which you can enter this node, this leftmost node. You will find everything inside this strongly connected component, but you can't find anything else because you second DFS goes on the reverse graph, and from this connected component you can't go anywhere. So you will visit everything inside this node, this component. So you will mark everything inside this component, but you can't go out of this connected components since you don't have any ingoing edges. So you will visit only this strongly connected component. Java something. It's not about Java. It's not about Java. This lecture is not about Java. Let's talk about algorithms. Now you take the next node. So you take the leftmost node, which doesn't belong to your connected component. So it belongs to another connected component. This second connected component may have ingoing edges only from this component, only from this first one. So you may have ingoing edge only from here. You can't have ingoing edge from somewhere else. Because it is the leftmost node in this order P. So you take this node, again call the second DFS, it will mark all the nodes inside this connected component, but it can't go out of it because you can only go out to here, but these nodes are already marked before. So again, you will visit only the nodes inside your strongly connected component, and so on. Again, it's exactly like what in the topological ordering. So every time you take some component which doesn't have any ingoing edges. So you will visit only the nodes inside this strongly connected component. You can't go out of it. That's all. Now again, you take the next connected component. Again, you may have only edges from here. So you will mark everything here, but you can't go out, and so on. So each time you call the second DFS, you will mark all the nodes inside some strongly connected component, but you can't go out of this strongly connected component, since it is the leftmost component in this order. That's all. That's the whole proof. Yeah. Nice. So this is the whole Kosaraju algorithm. What is the time complexity? No, time complexity is easy. So what we do in this program, we run first DFS, reverse, run second DFS. So all the actions are actually linear. So the time complexity of this algorithm will be linear. So time complexity will be, let's say, n plus m. That's all. That's how you build the strongly connected components. Whew. Okay, we have 30 more minutes to discuss two subproblems. You can watch any lectures you want. So just watch everything you like. So if you have some algorithm you want to learn, just watch every lecture about this algorithm. Some lectures are different, so maybe my approach will be harder to understand than some another approach. So try to watch all the lectures and find what works for you. Actually, for the most of complicated algorithms, usually you can't understand them from the first try. You need some different approaches to understand actually what's going on. Actually, sometimes it's better to watch the same lecture twice just to find all the details you missed on the first try. So just cool. TwoSat. So one of the coolest applications of this technique is to solve the TwoSat problem. So what is TwoSat problem and how to solved. So, two-side problem comes actually from Boolean algebra and stuff like this. So it's one of the problems which comes from this Boolean logic and stuff. One of the most classical problem of this, of the Boolean logic. So the problem is like this. You have the Boolean formula of the very specific type. The Boolean formula must consist of several clauses. And in each clause you have exactly two elements, like for example, x or y. So you have n variables, Boolean variables. And for each clause you have exactly two elements. Each element must be a variable or the negation of this variable. Like this. And you have something. Let's put something again. Okay, let's put it like first time. I already know what I want to do. Or z. And let's say not z or not x. Something like this. That's all. So you have a formula, you have n variables, and you have formula like this. In this formula you have clauses. In each clause you have two elements. Each element is a variable or negation variable. That's all. And the question is it possible to assign some values to all the variables so this formula will be true? That's all. It turns out it's quite surprising that a lot of problems actually turns out to be reduced to two-side problem. So there are many different problems from various fields which can be reduced to solving some long two-side problem. Another interesting thing that if you look on the not two-side problem but three-side problem, if you allow three elements in all these clauses, it will be NP-complete problem. So if you allow three elements in all clauses, it will be NP-complete. But if you allow only two clauses, it will be polynomially solvable, but and actually linear in linear time. I'll just erase everything, just to have some space. Any more questions by now? Yes, we need to check if this Boolean formula is satisfiable. So we need to find some values for all variables, so this formula is true. No, okay, let's try to solve it manually. So what will happen if you try to solve two-side problem manually? Let's take some variable. Let's take variable x. For this variable x, you have two options. You can assign 0 or 1. Yeah? Let's try to assign 0. So if x is 0, what happened? So if x is 0, then for this clause, yeah, this is false, so this must be true. So if x is 0, then y is definitely true. Now, we know that x is 0, y is 1. Let's look on this clause. For this clause, we have false here, so this must be true. So z must be 1. Now for this clause, we have here we have false, here we have true. So all the clauses are satisfied. That's all. Easy. Yeah. No, basically what happens, we just guessed the solution for the first variable, and then everything is uniquely determined. No, on the other hand, so if you say that x is 1, that will happen. So if x is 1, then in this clause, this is false, so this must be true. It means z must be equal to 0. Yeah? So z is 0. If z is 0, then in this clause, you have z equal to 0, so y must be 0. So y is 0. That's another solution. So we have two different solutions for the same formula. That's normal. So sometimes you have several different solutions for the same formula. The question is to find any valid solution for this formula. Actually, classical problem is to check if this formula is satisfiable or not, but we will actually find the solution. So our algorithm will find the correct values for all variables, which give the true in the Whew. Okay, I'm just doing it very slowly to give you some time to rest. Go. Oh, let's have some more examples. For example, what will happen if we have something else? Let's say, so we have, for example, not y or not x. Yes, the number of different solutions may grow exponentially. And actually, to find the number of different solutions is, again, something complete problem. So you can't find the number of different solutions. You can't iterate over all different solutions. The question will be to find any solution. So our algorithm will find some solution for this problem, if it exists. So what happened in this case, for example? Let's try to do the same thing. So we'll try assign x to 0. If x equal to 0, then let me mark here. Then this is 0. Yeah. So this must be true. So y must be true. If y is true, then this is 0. So this must be true. Yeah. So z must be true. Now here you have not z, so you have 0 here, but 1 here. So this clause is fine. In this clause, you have not y here, so it's 0 here. Let's put here, like this, and 0 here. So here you have contradiction. Yeah. So again, we assume that the value of x is 0, and try to find everything which is from this. So from this, you get that y must be 1. From this you get that z must be 1. And now all the values are fixed. And you have a contradiction here. So x may not be 0. So you have a bad case here. But if you try x equal to 1, then it will be fine. Because if x equal to 1, then you have 1 here, 0 here, 1 here. So in this clause, z must be 0. So this is 0. So y must be 0. 0. Now this is true and this is true. And now it's fine. Yeah, yes, in this problem, all the brackets have exactly 2 variables. That's yeah. Again, in the common case, so if you just look on any Boolean formula and try to find this value, it is an incomplete problem. So for all Boolean formulas, it is an incomplete problem. And even if you allow 3 variables in each clause, it will be an incomplete problem. So this is very special problem which is actually solvable. It's a rare case. Okay. Okay, let's go to the algorithm. The algorithm will actually do the same thing we did manually. So what will happen? So we will try to find all the implications for some variables to another variables. For example, let's look on this first clause. For this first clause, we know that if what happened in this first clause? in this first clause, if we have not x, then we have y. And vice versa. So if we have not y, then we have x. So each clause will give us two implications like this. For example, here again, you will have if y, then z. So if this is false, then this must be true. And if not z, then not y. And so on. So each clause will give you two implications like this. Nice. So what we'll do? We will build a graph. It's a lecture about graphs, right? So we will build a graph. In this graph, we will have two nodes for each variable. So one variable, one node will be correspond to value true, and another for value false. So here will be x, here will be not x, y and not y, z and not z. And now we just will add edges corresponding to this implication. So for each clause, we will add two edges to our graph. Edges will be like this. Each edge corresponds to some implication. So if this statement is true, then this statement must be true. Well, let's add all edges. So here we have if not x, then y. If not y, then x. For this clause we have if y, then z, like this. And if not z, then not y. For this bracket we have if z, then not x. So if this is false, then this must be true. If z, then this is false. Yeah. So this must be true. So if z, then not x. So if z, then not x. We have edge like this. And if x, then not z. And for this clause we have if y, then x. And if not x, then not y. That's all. We can have or outside the bracket and it inside bracket. No, you can think about it. So if you have ors in these places, it's actually pretty it's quite a stupid problem actually. So if you have ors here and adds here, you just need at least one bracket to be true. So you take any bracket, make it true, and that's all. So it's actually a problem. Yeah, it's so called I don't know how it's called in English. So it's my conjective normal form. It's some normal form of the formula. It's not important how it's called. Important is this graph. Let's look at this graph. Now, so in this graph, we will try to find the contradictions. So what's contradiction? Like we see before. So if you, for example, if you assume that x must be equal to 0, then y must be equal. So if equal to 0, then 0, then y must be equal to 1, then x must be equal to 1. That's a contradiction. So if x equal to 0, then x must be equal to 1. But that's not the problem. It just means that we didn't guess the value of the x. So if from x equal to 0 implies that x must be equal to 1, it just shows that we picked the wrong value for this x. But what is the problem? How can we say that this formula is actually impossible to satisfy? What is the easiest way to see that this formula is actually not satisfiable at all? Can you see it? So, in what case it's very easy to see that this formula is not satisfiable. Yeah, it happens when you cannot put any value for some variable. So if you take some variable, try to put value 0. So you try to put value 0, and it implies that x must be equal to 1. Then you try value 1, but it implies that x must be 0. So if you have these implications in both ways, it means that you can't assign any value to this x. It means it is impossible to satisfy your Boolean formula. Yeah, you already found the next step. Now we need to check if for some variable you have these both paths. So in this graph, what should happen? So you must have path from x to not x, and also a path from not x to x. How to check this in linear time? We already did this before, yeah. So to check this case in linear time, we just build the strongly connected components in this graph. And if you have these two vertices belong to the same strongly connected component, then you have a problem. So you build the strongly connected components for this graph. And if you find both these vertices belong to the same strongly connected component, then it is impossible to satisfy your Boolean formula. Yeah, that's all. We just learned how to build strongly connected components in linear time. So we just apply this algorithm to this graph. So they belong to some strongly connected components. So if you have a situation like this, it is impossible to satisfy your Boolean formula. And the interesting thing, it turns out that it's the only case when it's impossible. So if you don't have a case like this, so for all these pairs, these two vertices belong to different strongly connected components, then the formula is always satisfiable, and we will find the solution in a few minutes. Yes, yes. Now you can see why it's not happening, why you can do the same when you have free variables. If you have free variables, you can't make edges. So if you have two variables, you can make a cache like this. But if you have free variables, then you can do it. Yeah. Well, let's do it on this graph. So let's take this graph and find strongly connected components. Now, for example, in this graph, you have this cycle, right? This cycle. It is connected component like of these three nodes. Yeah, let's call it A. And you have this cycle. Let's call it not A, because of reasons. And now we will build the condensation of this graph. So what happens if we just condense all the nodes of the same component into a vertex? So we have this component node A. We have this component A. Let's make it bigger actually. Just put all the variables just to see what's going on inside this kind of component. So we have this kind of component node A. We have this component A. Yeah. And we have this thing belongs to some kind of component. So this expression, let's say this node X, Y, and Z. Node X, Y, and Z belong to this component, and this X, node Y, and node Z belong to this component. And we have this edge. We have this edge from node A to A. So let's put it here. We have this edge. Now let's see. That's all preparations. Now let's see what's going on inside each strongly connected component. So if you have strongly connected component, then you have implications from any statement to any other statements. So inside any strongly connected component, if at least one of these statements is true, then all statements must be true, right? Because in strongly connected components, everything implies everything. So if at least one of these is true, then everything else also must be true. So in every strongly connected component, everything is true or everything is false. Good. So what we'll do, we will build the same problem, but only on components. So instead of solving this problem, we reduce this problem to smaller problem, to the same problem, but on this condensation. So in this condensation, you have problem like this. Yeah, again, I'll build here. So you have only one variable. It will be true or false. And you have this implication here. So again, you try to solve this problem. You condensate each strongly connected component into a single vertex. Now you have this problem. This is the same problem. This is a two-sat problem. Yeah, but you have only one variable here. No, you may have more variables. So each strongly connected component is a variable. So here you satisfy everything here, or you satisfy everything here, and you have this implication. So it's easy to see what's going on here. Well, let's stop here for a second. So what's going on in this example? In this example, you can satisfy everything here, or you can satisfy everything here, and you have this implication. So if you have implication from something to something, and one of them is true, one of them is false, then what you want to do is to make everything here false and everything here true. Right? That's how it works. So the correct solution for this problem will be to make everything true in this group and everything false in this group. So x must be true, y must be false, z must be false. Cool. Okay, you're too quiet. Say something. How to decide which is true is false? That's the next question. That's interesting. Let's see. So what's going on next? Let's see. Again, here I moved that I named one of the component A and another not A. And I kind of imply that the set of variables here is the negation of set of variables here. Let's prove this. So I want to prove that all the components are split into parts, and you have situation like this. So in some component you have something here, and here you have a negation of this. So you kind of have the same situation here. Let's prove this. It's simple. So our graph is very specific here. This graph is very specific. It's actually called skew symmetric graph. It doesn't important. It's not important. What is the specific of this graph? Is all edges of this graph come into pairs. So you have these pairs of edges. So for each edge, you have a paired edge here. Let's see. So the specific of the graph is the following. You have all the vertices are split into pairs. So for each vertex, you have a paired vertex like this. And if you have some edge from U to V, this, then you always have a paired edge. So we have a symmetrical edge, but it goes in opposite direction. So if you have edge from U to V, then you also have edge from not V to not U. That's just specific of this graph. Yes. So I claim if my graph is skew symmetric like this, then all the components will also come into pairs, come as pairs. Yeah. So you have only strongly component will be grouped into pairs like this. Let's prove this. So let's have some connected components. So you have some strongly connected component A. In this component, you have two nodes, let's say, like this. You have some two nodes, V and U. they belong to the same strongly connected components. Let's prove that the symmetrical nodes for these two nodes, nodes node V and node U, these two nodes will also belong to the same strongly connected component. So if you have some strongly connected component and take any two nodes in these strongly connected components, then the symmetrical nodes will also belong to some strongly connected component. No, it's just specific of this graph. So in my graph, all the edges come in pairs, because I build graph like this. So I build this graph using these clauses. Each clause gives me two edges. One this, another this. Yep. No, basically, this is a graph of implications. If from U, this is if U is true, then V is true. And this says if V is false, then U is false. It is the same statement, right? So you just, because this graph comes from this formula, you have this property. Yeah. So what I want to prove? I want to prove if my graph is like this, then the strongly connected components come in pairs. So if you have some strongly connected component, you have some symmetrical strongly connected component. Now, let's prove. So you have these nodes V and U. They belong to the same strongly connected component. It means you have some path from V to U and some path from U to V. Let's find the symmetrical path. So you have path from V to U. If you look on these edges and find the symmetrical edges, they will move from node U to node V. So if you look on this path and find the symmetrical edges, you will get path from node U to node V, like this. And for this path, you have path from U to V. Again, for this path, if you look on symmetrical edges, you will get path from node V to node U. So if you have these two paths, then you have these two paths. So if these two nodes belong to the same strongly connected component, then these two nodes also belong to some strongly connected component. That's all. So nodes of if you look on all nodes inside this component A and find the symmetrical nodes, they belong to some strongly connected component node A. Too hard. No. Again, that's quite intuitive. So you have some statements. Everything in strongly connected components, all the statements imply each other. So you have this group of statements. The statements are all true or all false. If you look on negation of these statements, so of these statements, so this is just the opposite statements of this. If you look on these statements, they also must imply each other. It's actually quite intuitive. So if everything implies everything here, then everything must imply everything here. It's just how logic works. That's all. Now, I also claim that the condensation will be skew-symmetrical also. So if you have some component A and you have edge to component B, then you also must have edge from node B to node A. So if you have edge like this, then you must have edge like this. No, it's easy to show. So if you have edge like this in strongly connected in the condensation, it means that in your initial graph there was some node here, and you had edge like this. Now you look on the symmetrical nodes for these two nodes. There will be node here, and you had edge like this. So if you have edge like this, you have symmetrical edge like this. So in the condensation, you have symmetrical edge like this. Yeah, that's all. So my condensation will also be skew-symmetrical graph like this. Okay, let's stop here for a second. what happened? I had this graph. This graph was very specific graph. It was constructed from this formula. It has very specific property like this, because it's constructed from this formula. I made a condensation of this graph here. This condensation is also skew symmetrical graph because of this. And now I need to solve the same problem for this condensation. So I reduce my problem to this problem. But the problem is the same, but I'm working not with single variables, but with these connected components. Cool. That's almost all. What's the benefits? Why did you get from here to here? We have the same problem, but it's much better problem because this condensation is acyclic. Again, so what we did, we get rid of all the cycles. So now we have a cyclic graph, and we need to assign values 0 and 1 in this acyclic graph. It's very easy. So it's the final part. So how to assign values in the acyclic graph? You just build the topological order of this graph and assign values in the topological order. I need to erase something. I need to erase this. Sorry. I need to erase this. Okay, let's make some examples. So we have some condensation. Let's have, for example, A, B, not A and not B. And we have some edges, say from A to not B, from B to not A. And let's say not this, so from A to B and from B to A. So let's have you have condensation like this. So you had some graph and you have condensation like this. What you will do next is to build topological ordering for this graph. So we just run the top sort algorithm. It's actually if you run Kosaraju algorithm, it will give you strongly connected components in topological order. So you don't need to run third depth first search to make a topological ordering. So Kosaraju algorithm will return you strongly connected components in topological order. So you can just use this. So you make topological sort for this graph, for example. So you have A, let's say B, then B, then for example not B, and then not A. So this is the topological ordering of this graph. So we have edges from A to B, to not B, from B to not A, and from B. Like this. That's all. Now it's the final part. Using this topological order, it's very easy to assign values. Let's look on each component. Let's look on the pair of symmetrical components. We just assign left one to 0 and right one to 1. So for this A and not A, we assign 0 to A and 1 to not A. That's all. Now we take this B. So B is to the left, not B is to the right. So we assign B to 0, not B to 1. That's all. Now we'll prove that this is correct solution for the formula. For example, in this case it was simple. We had only one variable, so we have 0 and 1. If you have more than one variable, it may be a little bit more complicated. That's all. That's all. I'm just waiting for your questions or something. Again, the whole algorithm works like this. You build this graph, build strongly connected components, build the condensation. Now you take this condensation, make a topological ordering. And in this topological ordering, make look on the pairs of symmetrical components, assign 0 to the left one and 1 to the right one. And this will be the correct solution. Cool. Now, final thing, let's prove this. It's actually simple. How to prove this actually correct solution? Let's look on the leftmost variable. So we have this topological ordering. Again, let's look on the leftmost variable in this topological order, on this A. It is the leftmost variable. So it is leftmost vertex in topological ordering. So it must not have any ingoing edges. So you have this topological ordering. You take the leftmost vertex in this topological order. It has no ingoing edges. It has only outgoing edges. So if you assign value 0 to this variable, all these implications will be satisfied, because you can imply from the 0 you can imply anything. So all these implications are satisfied. Now let's look on symmetrical variables. So this will be A, this will be not A. Not A is not always the last in this order. It may be in the middle of this array. That's fine. What is true that if this A has no ingoing edges, then this not A should have no outgoing edges, because the graph is skew-symmetrical. So if this not A have outgoing edge, then the symmetrical edge for this will be going inside this A. So you can't have this edge, because you will have symmetrical edge like this. Now, since this not A have only ingoing edges, if you put value 1 here, then all these implications will be satisfied, because you can imply 1 from anything. That's all. So all these satisfied, all these satisfied. Now we just remove this A and continue the same process. So you take the next. So again, you take this leftmost node. This is satisfied. This is satisfied. This is satisfied. This is. Now just remove this A from your graph and continue the same thing. Take the leftmost node. Everything is satisfied. For the symmetrical one, everything is satisfied, and so on. So you continue this process and just prove that all the edges will be satisfied. That's all. Okay, that's the whole algorithm, and it's obviously linear. So the hardest part for this algorithm is actually to construct this condensation. After you construct this condensation, you just build this topological order and assign the values. That's all. So the hardest part of this algorithm is just to build this condensation, and we just show how to build condensation in linear time. So this whole algorithm actually works in linear time. You can imply y from anything. It will be true. You can say if 0 then 1, it's correct, it's true. If 1 then 1, it's true. So that's cool. That's correct. So you can put anything here, and this will be correct implication. That's all. Again, you can look at it like this. Let's look on any clause here. So for any clause, so let's prove that this actually solves the problem. Let's look on any clause in this formula. For each clause, you will have some edge. This edge actually guarantees that this clause will be satisfied. Each edge will be inside this strongly connected component. If it is inside, then both things are either false or true. So, for example, let's look on this clause, for example. So you have this clause, not z or not x. Yeah. From this clause, we made these two edges. So we made this edge and this edge. Okay. These edges are inside these strongly connected components. So we have edge from z to not x here, and another edge from not z to x, or from x to not z. These edges are inside strongly connected components. So for this edge, both these things are either true or false. We just build the solution. Right? If they both are true, like here, so we have x and we have not z. If you have them both true, it means that, like here, then one of them will be false, one of them will be true. So each clause like this will be satisfied. And if you have clause like this, less from not x to not z, so it's fine. Just look, if you look on this clause, you will have this edge. This edge actually goes from here to here. So for this edge, we have either this true or this false. So if you have this true, then you will satisfy one variable. If this is false, then you satisfy another variable. So this edge guarantees that at least one of these things will be true, and so on. So if all edges are satisfied, then all clauses will be satisfied. That formula will be true. Okay, hope it's clear enough. Okay, thank you for joining me. See you next week.